Imagine a world where robots aren't just stuck on factory floors, but they're actually like helping us out in our daily lives, doing the dishes, maybe organizing your home, or even tidying up a busy cafe.
Yeah, that's been the dream for a long time in robotics, right?
Exactly. But the real world is just so messy, so diverse. It needs robots that are, well, really robust and incredibly dexterous. It's a huge challenge.
It really is.
So today we're doing a deep dive into something pretty groundbreaking from ByteDance Seed. It's a new system they call GR-3. GR-3.
And this isn't, just any robot system. It's powered by a large-scale vision language action model, a VLA model.
That's right. And GR-3 is showing some truly remarkable capabilities. We're talking really exceptional generalization.
Generalization, meaning?
Meaning it works well with new objects it hasn't seen, totally new places, and even like abstract ideas in the instructions people give it.
Okay, abstract ideas. Like what?
Like telling it to pick up the largest thing or put the marine animal away, stuff like that.
And what's also really compelling is how efficiently you can fine-tune it. It doesn't need tons of new human data, which makes adapting it way quicker and cheaper.
That sounds key.
It is. Plus, it performs incredibly well on really complex, long tasks, things that take multiple steps, involve using both hands, even moving around a room.
Okay, so our mission for this deep dive is pretty clear then. How on earth did they achieve all this? And, maybe more importantly, what does this actually mean for the future of robotics? Let's try and unpack it.
Let's do it.
All right, so at its heart, GR-3 is one of these vision language action models, VLA. The core idea seems simple but powerful, right? Robots see the world, understand our language, and then turn that into physical action.
Fundamentally, yes. It's a really promising direction for building robots that can do lots of different things, not just one task, generalist robots.
The VLA models usually hit some big roadblocks, don't they? Like following instructions with objects they've never seen or understanding those tricky concepts you mentioned. And they often need just mountains of training data.
Exactly, and that's what GR-3 tries to tackle head-on. Its foundation is built on a pre-trained vision language model, or VLM.
Okay, a VLM.
Specifically, Qwen 2.5 VL3B Instruct. You can think of that as like a really advanced AI that already understands both images and text pretty well, that forms the robot's basic grasp of the world.
And then it has to act, right?
Yeah.
How does it predict the actions?
It uses a technique called flow matching,
Right.
which basically helps the robot translate its understanding into really fluid, continuous movements, smoothly, not jerky, like how a dancer kind of anticipates their next move. And the whole GR-3 model itself, it's pretty hefty, about 4 billion parameters.
To a billion.
Yeah.
Now, you mentioned something interesting they found during training, some instability.
Yeah, that's a fascinating detail. They noticed the training was often unstable. Things weren't converging well.
Yeah.
So they tried applying this thing called RMS norm. It's basically a way to stabilize the calculations inside the network, but they put it after certain linear layers in the action prediction part.
And that helped.
It dramatically improved stability, yes, but here's the really interesting part. It also, somewhat surprisingly, made the robot much better at following language instructions in their real-world tests.
Just adding that stabilizer.
Yeah. It just goes to show how sometimes these, small technical tweaks, often found just by trying things out, can have these really big, unexpected benefits in complex AI systems.
That's wild. Okay, so that's the brain, the GR-3 model. But a brain needs a body, right?
Absolutely. And that's where ByteMini comes in. That's the physical robot they designed specifically to work with GR-3.
ByteMini.
And they really purpose-built this thing for versatility, high reliability, which is crucial, and also user-friendliness. They knew it would have to handle a lot, both for collecting data and just running the policies.
So what makes ByteMini special? What are the key features?
Well, it's a bimanual mobile robot, meaning 2 arms, and it can move around. It has 22 degrees of freedom in total.
22, that's a lot of joints.
It is. And crucially, the arms, they have 7 degrees of freedom. Each use this unique sphere wrist joint.
Sphere wrist.
Yeah, it sounds fancy, but it basically gives it much more human-like dexterity. It lets the robot work really effectively, even in tight, confined spaces where traditional robot arms might struggle.
I can see how that would be useful.
Definitely. Plus, the elbow design allows for what they call large internal adduction. That means the arms can cross over and work together closely right in front of the robot's chest. Really important for delicate two-handed tasks.
Okay, that makes sense.
Yeah.
And what about reliability? You mentioned that was key.
Right. So for mobility, It uses an omnidirectional platform, it can move any direction, and it has a lift mechanism, so it's stable, and it can adjust its height precisely.
Like raise itself up and down.
Exactly. And for the arms themselves, they use actuators based on the quasi-direct drive principle, QDD.
QDD.
Think of it like the motor is almost directly connected to the joint. It allows for incredibly precise, stable, and responsive control, almost like a direct line from the robot's brain to its muscle. Really helps with smooth, consistent motion.
Nice. And user-friendliness. How does that show up?
Well, it's got things like an integrated screen right on it, a small, powerful computer, an NUC built in, and dual batteries that give it over 10 hours of working time.
10 hours, that's pretty
Yeah,
well.
and there's a wireless e-stop for safety. Crucially, for perception, it has RGBD cameras. Those give color and depth information on its head and on both wrists.
Ah, so it can see things up close when it's manipulating them?
Precisely. Just like how we use our eyes to see depth. Those wrist cameras are vital for fine motor skills.
Okay, so how does the whole system actually control ByteMini?
They use what's called a whole body compliance control framework. It treats all those 22 joints kind of holistically. This lets them translate human movements captured during teleoperation into smooth, feasible robot motions.
And how do they do the teleoperation, the human control part?
They use Meta VR Quest headsets, so an operator wears the headset, and their movements are mapped pretty intuitively onto the robot's arms, its end effectors.
Ah, VR control. Makes sense.
And then, when the GR-3 policy is actually running the robot, they use trajectory optimization techniques to smooth everything out, minimize jerkiness, and make sure the movements are stable and efficient.
Okay, so we have this powerful brain, GR-3, and this capable body, ByteMini. But how do they actually teach GR-3 to be so good? You mentioned it learns efficiently.
Right. The secret sauce is really in what they call a multi-faceted training recipe. It's a clever mix of different data sources.
Okay, what are they?
So the first one is robot trajectory data. This is the classic imitation learning stuff. Humans teleoperate the robot, showing it how to do tasks, and the robot learns from those examples.
Standard imitation learning.
Pretty standard, yeah. But they used a scheduler to make sure they got lots of variety, different tasks, objects, environments. And crucially, they added this auxiliary supervision signal called task status.
Task status?
Yeah, labeling trajectories as ongoing, terminated, or invalid. By training the model to predict invalid for impossible commands like, say, put the knife in the basket, if there is no knife, it forces the model to pay really close attention to the language instructions.
Ah, so it learns not to act if the instruction doesn't make sense.
Exactly. It learns when not to do something, which is just as important.
Okay, that's clever. What's the second data source?
The second is web-scale vision language data. This is stuff scraped from the internet, image captions, visual question answering data sets, things like that.
Okay, how does web data help a robot?
It's used to co-train that VLM backbone we talked about earlier, the Quen model. And this is super important because it boosts GR-3's zero-shot generalization.
Zero-shot meaning?
Meaning the robot can understand things, objects, concepts it's never specifically encountered in its robot training data. It gets this broad, general knowledge about the world, understanding abstract ideas like marine animal or largest, just from seeing how humans talk about images online.
Wow, so it's like giving the robot common sense from the internet.
Sort of, yeah. A very broad visual and conceptual understanding.
Okay. And the third data source, you said it was highly efficient.
Yes. The third is human trajectory data. This is collected using VR devices. Specifically, they mention the PiCO4 Ultra Enterprise.
But how is this different from the robot trajectory data? Isn't it still humans moving?
It is, but here they're just capturing the human's movements in VR without needing the physical robot involved in the collection loop.
Ah. So you don't need the actual robot there while collecting.
Exactly. And this makes it way, way faster. They could collect around 450 trajectories per hour this way, compared to maybe 250 per hour using robot teleoperation.
That's a huge difference.
It is. It means you can adapt the robot to new situations or teach it about new objects really quickly and much more cheaply. It's a big deal for scalability.
Okay, so let me see if I've got this. You combine the robot demos for precise imitation.
Mm-hmm.
The web data for broad understanding and generalization, and this fast human VR data for quick adaptation.
You got it. That combination is what allows GR-3 to generalize so well, adapt efficiently, and perform these complex tasks robustly. It's a really neat recipe.
It really sounds like it. Okay, so they built this system, they trained it with this clever recipe.
Yeah.
How did they prove it actually worked? What about the experiments?
Right, the real-world tests. They set out to answer 4 key questions, really, about its capabilities. And importantly, they compared GR3 against what was considered the state-of-the-art baseline, a model called 0 pi 0.
Pi 0, okay.
And pretty consistently, GR3 significantly outperformed 0 on these challenging tasks. It showed a real leap forward.
All right, let's break them down. What was the first big test?
First up was generalizable pick and place. Simple sounding task. Put object A into container B.
Right.
But they made the settings really tough to push the limits of generalization.
How so?
Well, they had a basic setting with stuff the robot had seen before. Then unseen environments like a checkout counter, a break room, totally new places. Then unseen instructions.
The abstract concepts again.
Exactly. Things like put the largest object into the carton or put the marine animal into the carton, stuff that requires real understanding, not just matching keywords. And finally, unseen objects, 45 different objects, and over 70% of those were from categories the robot had never seen during training.
Wow, okay. So how did GR3 do?
The results were really striking. GR3 showed huge improvements. For example, with those unseen instructions where robots usually struggle, 0 got about 40% success rate. GR3, 77.1%.
Gobbled it almost.
Pretty much. And on unseen objects, it went from 0's 40% up to 57.8% for GR3. It really showed that the co-training with web data was paying off, giving it that ability to handle novelty.
Okay, that's impressive zero-shot performance.
Yeah.
But what about that efficient human data? Did they test that here?
They did, and this is where it gets really interesting. The few-shot generalization part.
Okay.
Get this. They took those 45 unseen objects. They collected just 10 human trajectories per object using that fast VR method. That's only about 30 minutes of total data collection time for all 45 objects.
30 minutes. That's it.
That's it. And with just that tiny bit of extra data, GR3's success rate on those unseen objects jumped from 57.8%, its zero-shot score, all the way up to 86.7%.
From 57% to almost 87% with just 30 minutes of human demos.
Exactly. And crucially, its performance on the objects it had seen before didn't drop at all. It just got much better at the new stuff.
That's huge. That makes adapting robots seem so much more feasible.
It really does. It points towards a very sample-efficient, cost-effective way to fine-tune these models for new tasks or objects.
Okay, pick and place is one thing. What else did they test? You mentioned long-horizon tasks.
Right. The second big test was long-horizon table bussing. Much more complex.
Table bussing, like cleaning up after a meal.
Exactly. The robot had to clear a messy table pack, leftover food, put utensils in a bussing box, throw trash in a bin, and this required it to actually move its base around the workspace.
Okay, multi-step involving navigation. Tricky. How did they set this up?
2 main ways. First, a flat setting, where they just gave a general command like clean up the dining table, and the robot had to figure out all the steps itself.
Fully autonomous completion.
Right. Then, the more challenging instruction following, or IF setting, here they gave it specific subtasks one by one in sequence.
Okay. And did they add any twists in that IF setting?
Oh, yeah. They included novel destinations, so maybe telling it put the fork into the rubbish bin, even though in training, forks always went into the bussing box. Tests if it's really following the instruction, not just repeating patterns.
Makes sense.
And maybe most importantly, those invalid tasks. Again, instructions like put the blue bowl into the plastic box when there was no blue bowl. Testing if the robot correctly refuses an impossible command.
Right. That ability to know what it can't do. So the results.
Again, really compelling. In that complex IF setting, GR3 achieved a 97.5% success rate.
97.5%. That's incredibly high for such a complex task.
It is. Compare that to 0, the baseline, which only managed 53.8%. It really highlights GR3's ability to strictly follow instructions, handle sequences, and deal with those invalid commands robustly.
And did they confirm what helped achieve that?
Yes. Their ablation studies where they removed parts of the system to see the impact confirmed that both the RMS norm tweak we discussed earlier and that task status supervision were crucial for these big gains in instruction following and robustness.
Fascinating how those pieces fit together. Okay, what was the third evaluation?
The third one tackled dexterous cloth manipulation, hanging clothes on a drying rack.
Ooh, cloth. That's notoriously hard for robots, right?
Yeah.
Floppy, unpredictable.
Extremely hard. So the task involved picking up a hanger, carefully putting an item of clothing onto the hanger, and then hanging the hanger on the rack. Lots of potential failure points.
I can imagine. How do they vary the difficulty here?
They had a basic setting with clothes it had seen, positioned normally. then a position setting where the clothes might be rotated or crumpled up, and finally an unseen instances setting with new clothes patterns, and even different types, like short-sleeved shirts when it was only trained on long-sleeved ones.
Okay, really testing its adaptability to deformable objects? How did it fare?
It did remarkably well, actually. They measured average task progress. GR-3 got 86.7% progress in the basic setting, still a very good 83.9% in the tricky position setting, and 75.8% even with the unseen instances.
That's impressive progress for cloth manipulation. Was there any specific part it struggled with?
Yes. They noted the trickiest subtask was consistently getting the second shoulder, the left one usually, onto the hanger properly after the first one was on.
Ah, why was that?
Often because the collar might be folded awkwardly, or sometimes the hanger itself would slip a bit in the gripper during the maneuver. It really highlights those fine-grained, real-world challenges that still exist with manipulating complex objects like cloth.
Yeah, the real world is fiddly. So, GR-3 is clearly a big step forward, but it's not perfect yet. What are the limitations?
No, definitely not perfect. It's important to acknowledge that. It can still make mistakes, especially with really, truly novel concepts or objects that are very different from anything it's seen. And like pretty much all methods based purely on imitation learning, it can get stuck.
It's like how?
If it makes a mistake and gets into a situation, a state that's way outside what it saw in its training data, it often doesn't know how to recover. Imitation learning teaches what to do, but not necessarily how to fix things when they go wrong.
Right. It only knows the paths it was shown.
Exactly.
So what are the researchers planning next to address that?
They're quite clear about future work. One direction is just scaling up bigger models, more training data. But crucially, they also plan to incorporate reinforcement learning, or RL.
Ah, reinforcement learning. Learning through trial and error.
Basically, yes. RL could give the robot the ability to explore, to try things out, and learn how to recover from errors or handle situations that weren't explicitly in its imitation training data. It could really boost robustness and autonomy.
That sounds like a critical next step, combining the strengths of imitation and reinforcement learning.
It could be the key, yeah. Getting beyond just mimicking demonstrations to actual problem solving and recovery.
So, wrapping up on GR-3 itself.
Overall, GR-3 really does feel like a powerful step towards that dream of generalist robots. Robots that can genuinely help us with lots of different tasks in our messy, real-world environments. It's the combination of the vision language understanding, the efficient learning, and the capable hardware. It's a very holistic approach.
Yeah, it's been a really fascinating deep dive thinking about GR-3, the ByteMini robot. Some of those moments really stand out, like the unexpected benefit of that RMS norm tweak, or just how incredibly effective that multifaceted training recipe is, especially the efficiency gain from the human trajectory data. It really changes how you think about training these things.
It does. And as we see these systems like GR-3 getting so much better at learning from just a few human examples and generalizing to new situations, it definitely raises a big question for all of us, doesn't it?
Which is?
Well, what are the deeper implications as these incredibly capable robots start moving into our daily lives? What new roles might they actually take on? Roles we probably haven't even imagined yet. It's something to really think about.
That is definitely food for thought. What happens when robots can learn almost as fast as we can show them? Okay, on that note, that's all the time we have for this deep dive.
Great discussion.
Until next time, keep digging deep and exploring.